Hello, everyone. Welcome to class 5 of the machine learning course. Before we begin, let me read this ACM SIGGRAPH policy against harassment. This live stream is moderated by ACM SIGGRAPH. We ask that all comments stay respectful of others and respect ACM's policy against harassment. This means to exercise consideration and respect in your speech and actions. Refrain from demeaning, discriminatory, or harassing behavior and speech. And please be mindful of your fellow participants. All right, so let's begin. Welcome back to the course. So those of you who have been following along, we are in class 5, and we have a lot of interesting stuff to cover today. And before we get to that, I have a guest today, Ming-Yu. So Ming-Yu is a research scientist at Nvidia, and he has done a lot of interesting stuff with generative modeling using machine learning and neural networks. And first time when I saw one of his implementations from a paper about GauGAN, and that was something that was super cool, and I always wanted to kind of talk to him about it, and then I learned a lot from that paper about GANs in general, and then to try to create new images from existing training sets. So let's go ahead and bring Ming-Yu in. Hi, Ming-Yu.
And thanks for having me here. It's glad to be here.
All right, welcome to the course. And what we have been doing is we've been talking to a number of researchers, and as I said before, I think my interest in GANs goes back to when your first paper came out about GauGAN and being able to do that kind of interesting things with the machine learning really inspired me to get into the field. So I want to talk to you a little bit about like how you got into the field, what your background is, and what you're doing currently.
Sure. Yeah. So to be honest, I started as a researcher. I want to focus on computer vision and machine learning. I want to recognize scenes in the image. And that's the old school of thinking in the recognition community is if we can build the generative model of the world, and then we can use the generative model to understand scenes, to classify scenes. So I've been have a little bit of exposure to these the generative models, and I mean in the past we were using something like a energy-based model or some kind of other subspace method, but after attending the NeurIPS conference in 2014, where I learned Ian Goodfellow's work on GANs and take some kind of first-hand experience implementing that, and start to realize that it can be used to solve a recognition problem, but itself has a lot of interesting problem, the synthesis part. And then later I joined Nvidia, a company where focus a lot on synthesis, and I start to see more applications, and then kind of more dedicated to see how GANs can help with others to help others to synthesize beautiful images, videos, and 3D content. Yeah, so it's kind of built upon the belief that if we have good generative models, not only we can recognize the many content in the world, we can also create new contents. And hopefully, eventually, the model is smart enough and can help us create new things that people may not think about in the past. Yeah, so that's how I entered the field, and yeah.
No, that's awesome. So, and we'll cover Gans in detail a little bit later today. But can you give us your view of first, what the original paper about GAN, what was it about, and then how you implemented GauGAN on top of it, what kind of differences or changes you had to make?
Sure. Yeah. So GAN is a model where the objective is to be able to synthesize distribution of images that is similar to the target distribution of images. So so it uses a generator to convert a Gaussian noise to another distribution, and hoping that this distribution is similar to the data distribution used to train the GAN. It has a generator and discriminator. Generator, as I mentioned, is used to transform the distribution to the target one, and discriminator is to make sure the output image looks like sound coming from the target distribution, the data distribution. So this is quite different to some kind of maxima likelihood learning based methods, like where you have a target, you want to reconstruct the image. Yeah. So and I think the advantage is that you are looking at the output from a distribution point of view, not specific to a sample. And then I feel like this actually help GAN to kind of synthesize better images, and in the expense of sacrificing some sample that it may not be able to generate well. Yeah, so it kind of a good trade-off if you focus on synthesis. Yeah, and GauGAN is in the class of conditional GANs. Instead of having a random Gaussian as an input, you have some kind of other representation, like a segmentation mask sketch. So in this case, instead of learning unconditional distribution, you learn a conditional distribution. So given a segmentation input, you want to convert it to a real image that will resemble the target output distributions. There are a couple of works before GauGAN focusing on the problem, and I think what GauGAN really bring to the field is a new modulation layer called SPADE, especially actually the demodulation layer. I probably shouldn't get into the detail, but let one solve some kind of problem in converting segmentation to image, and it allows us to synthesize better images and to build a GauGAN demo.
Okay, no, that demo was awesome. I think I was at the Nvidia conference one time and saw it live there. So are you using multiple models in that demo, or is it a single model?
It's a single GauGAN model.
I see. And then the inputs that you provide, those are the conditional things that you brushstrokes that you provide.
That's correct.
Right. And then are there any more works in that area of putting a person in the loop to kind of, because this conditioning thing happens at the beginning, right? But is there other ways to change or affect the output for more artistic controls?
So I can think of a couple of approach to further improve the outputs. For example, sometimes people want artistic outputs. You can combine with some kind of style transfer network to make them more like a Van Gogh's painting. And I think there are also people trying to get more 3D output. So yeah, so those are possibilities.
That's awesome. So thank you. And then for what is your current work involved now? What kinds of things are you doing, if you can tell about?
Sure. So more recent project is called GanCraft, and so our vision is that Minecraft is one of the most popular games that ever built. and it's again of 3D content creation. People kind of build blocks there, and those blocks, they have semantic meanings: human, mountain, river. And so in GauGAN, we try to see if we can directly synthesize realistic 3D environments by just taking the Minecraft output. And there are a couple of challenges. I mean, with the GauGAN model, we could map one particular projection of the 3D world to some realistic image, but it's environments. People change viewpoints, and there are objects moving, and so. And we need to make it a valid environment. We need to measure when you rotate the camera, the same object look the same. There's no temporal flickering. Yeah. So and in the GauGAN work, we are exploring another recent advancements in neural rendering called NERV, neural radiant field, and try to leverage the representation there to get the view consistency, kind of combine the advantage of GAN on hallucination content and the ability of NERV to give view consistent outputs. So that is an ongoing project. Yeah, and of course, it's still a long way to go. And hopefully we have more results to share in the future.
Right. No, that's super exciting. I'm looking forward to seeing what you guys come up with next. And then as last few minutes, do you have any advice for people getting into the field? Like what kinds of things to focus on? I know everybody likes the shiny new models, but any other advice on like how to learn and how to do things with machine learning to get into the field and get experience?
Yeah, so I think it's a great question. I feel like when working on generative model, the most difficult thing is evaluation. So how do you know you are making progress? So usually when start a new project, I will try to first brainstorm how I gonna measure the progress of the projects. There are a couple of good metrics like FID and precision recall that is useful. So I would suggest a newcomer to take a look at those metrics and understand the meaning of the score and how the significance of improvements. And the second thing I think it's useful is GAN is still kind of unstable to train, and many implementation details matter. And when you use normalization techniques, the involved division, sometimes you need to be more careful on the numerical issues. So pay attention to that part. Sometimes a model fail can be easily fixed if you do some kind of proper conditioning. Yeah, so it's an exciting field, but take some time to find the small trick to make it work, and just be patient and try hard, I would say.
That's great. Thank you again. Thank you for being with us today, and I hope to read more about your work later on.
Thank you so much. Thanks for having me here. Bye-bye.
Bye-bye. All right, so let's get back to the class. So I seem to have deleted my tab, so let me bring that up. Are you still able to see my slides or not anymore? You are. So I'm still trying to find that tab. Just hold on for a second. Let me. Something weird is happening. Sorry. Okay, we have it back. So today we are going to do a quick recap. So let me make this smaller because when I make it larger, I don't have access to the other tabs for some reason. But let's go with this. So we're going to do a quick recap of distributions and autoencoder, and talk about transfer learning and pre-trained models and variational autoencoders, and then we'll talk in detail about GANs, as Ming was describing. So log into the Google Drive, make a shortcut to it, and then make a copy of all of these files we are going to be covering in some way or the other. And let's get to it. We have a lot of stuff to cover, and I'll come back to some of these things later on. So we talked about autoencoders a couple of classes ago, and we said that we can take a dense network like this, and we can squish it down in the middle. And when we do that, we are essentially compressing the input down to some encoding. And that encoding, also known as latent space, it will give you a compressed view of the input, and you can then try to recreate that again with a decoder, which is just the mirror image of the rest of the network that you had in the beginning. So once you do that, you're able to reconstruct the data, and there is some loss, but it's you can adjust how much you want to compress and how much loss you want to tolerate between the input and the output. So you get nice little view of what things are. So what it means in practical terms is that if you have an image of, say, this handwritten digit 4, and you encode it into some compressed format, and then you decode it, it will look like the original. There'll be some loss. And we can use this to our advantage by training things. If we take the loss as a metric, then we can input a clean image and a noisy image, and then try to recreate the clean image from the noisy image by training it. So this is how the autoencoder worked, and ultimately we were able to produce some images like that. So, so what happens in the latent space area is that you have these distributions of these digits that are somewhere in this latent space. It could be high dimensional. In our case, it was down to like a few nodes, but it could be any kind of high dimensional latent space that we don't know the distribution of. We just know that these things are in there, and then once you expand it back, you will get back a representation of the original. So that's good, but I think we want our latent spaces or in between layers to have some meaning. We want to be able to kind of see how the network is learning. So so the other kind of network that was devised to kind of achieve that is called CNN. So CNN kind of works like, you could think of it as like a human vision system or human perception system, where we learn by understanding small little things and then group them into bigger structures and so on. So at some point, you'll have this hierarchical representation of an image. So when we are looking at an eye, you would see it as composed of small little parts. And then as you make up the hierarchy, you can see the retina part of it, or the pupil, or other parts of the eye as bigger structures. And as you go on, you see the whole eye. So you can think of breaking up an image into its constituent parts, or going in the reverse way, where you're trying to understand the image, how it is composed of its smaller parts. So CNN is a neural network that is designed to kind of process images that way. So a convolution, the convolution is an older process that comes from like when you convolve the images, you take a filter. You take a filter of like a small size, and then you run it over the image. So it kind of looks like this. So here the greenish box is a 3x3 filter that is going over the image 9 pixels at a time, and it shifts a little bit. And this kernel, the 3x3 pixel patch, it has some weights in each of those pixels, and they are applied to the underlying image, and then you average those. So that way you can keep doing that throughout the image, and then you represent, you kind of get a averaged view of the image. And if you do this repeatedly, you can start seeing structures. So at some point, you also want to start compressing it. So when you move by 1 pixel at a time, you are basically taking 9 pixels and outputting 1 image or 1 pixel. So that way you get this 9:1 compression in the network. So if you do this successively many times, you can start seeing these different features of the image emerge. So what we will do today is try to build this up like a CNN network, and then we will try to denoise images. So denoising, as I spoke last time, is the process of taking an image that is degraded in some way, and if you have a clean version of it available to you, as in a ray traced rendering system, you would have that readily available at a different samples per pixel level, and you can train that to start being able to recover a clean image from that. So you do this repeatedly, and it works pretty well using a modified version of a CNN. In many cases, you may not have a noisy image, because if you're not using a renderer, where do you get the noisy image? So what you can do is you can create a noisy image manually by just like introducing noise. So that noise has to be kind of representative of the kind of noise you want to eliminate. If you train it for random noise, it will eliminate random noise. The ray tracing noise is a special kind of noise. A camera noise is a little bit different kind of noise, the CCD cameras. And then, so this is applicable to not just denoising, but you can do other kinds of things with it. So we talked a little bit about that we can try to remove some tint with it, so or do some in painting. So if your image has kind of small holes, you can fill them up, kind of like what Photoshop does. You can do dirt removal. You can even try to colorize, and colorize is, you'll figure out like it's hard to do, because it will kind of like smooth things out. That's what CNN, the convolution does. It smooths things out a little bit. And you can do upresing. And upresing and in-betweening, they work pretty well too. You can have a low-res image and produce a high-res image. So all these networks are some form of a convolution neural network. And we will build one, a simple one for denoising today. So let's take a look at the denoiser. The denoiser CNN.pyn, and let me make this bigger so you can see it. Any questions so far while I adjust my window? Okay, let's keep going. So we're going to use TensorFlow, some packages to import, and we are going to download this satellite images. So we talked about these satellite images. They're available as a TensorFlow dataset. And we also talked about last time TensorFlow dataset on how to build that up, how to make batches. And I also introduced you to how to make patches out of each image and then process those patches to introduce noise. So this might take a little bit of time, and I'll take questions in the meantime. Okay, looks like there are no questions, so let's keep going on. So it looks like the data set is loaded, and we'll find the information. So again, it's a satellite set of satellite images, about 2,100 of them, and we have some features in there. So this is classified data, classified in the sense like it has classification. It's not classified satellite images, but it has some classification where the labels are given. We won't use the labels because we are just interested in the images. So we're going to create patches out of each image of 128 by 128. Let's just look at some of the data, and it's just set of images from satellite, and they're labeled. So these two functions, extract patch and add noise, they are first going to extract 128 by 128 patches from the image, and they will add noise. And this is just a random normal noise with some standard deviation that we added. So this is how much noise you want to add. And it will give you a noisy image and the original. So, and then we set up our pipeline. Execute these. And we will separate some data for training and for testing. And so this is the part which basically extract the patches and adds the noise. We're going to set up for testing as well. So in the testing part, we don't do patches, we do full size. That's why we have 256 or 256 here. And so all the setup that we do in this pipeline, nothing happens. It just sets up the pipeline to be executed later. And pipeline only gets executed when you have some statement like a take here, or when you actually train. So let's do the take of 5 images, and we're going to plot both the noisy part and the original part. So let's take a look at that. So that's some of the images that we have that with noise added in. So now we're going to train. So we have now ground truth, which is a clean image, and the noisy image. So again, these are patches from the original images. So we're going to shuffle and batch and then process. So this is great because TensorFlow takes care of all of this. Even if your data did not fit in memory, it will figure all this out. It will prefetch some data. It will shuffle the data automatically. It will make your batches. It will repeat as necessary to get the number of epochs you want. And so So even just by these few lines, you are essentially, you can train the same thing on a cluster or on the cloud, and it will use all the available resources to do this as efficiently as possible. So this is a lot of bulk of the time people spend in kind of optimizing their pipelines, because the training takes a while, and so you want to be as optimized as possible. So here is where we'll create the convolutional neural network. And all we're doing is essentially creating 3 layers of convolution. And the first argument is the number of nodes in the network. And the second argument is the kernel size. So that's all we need to do. Let's build it. And just as a comparative thing, let me show you an example where you can also create an autoencoder model. So remember, autoencoder model was fully connected, and you can do denoising with an autoencoder. It's totally fine. But you'll see the difference in the sizes of these models. If you look at the CNN model, the number of parameters is 21, and then for an equivalent autoencoder, the number of parameters is like in the millions. So because the convolution is kind of compressing the image in a way where the convolution operation itself, based on the size of the kernel, will average out the pixels. Whereas the fully connected network is fully connected, and each node is connected to each other node. So you get significant amount of nodes there. So, but the competition is not less. The convolution layer, it does a lot more than the autoencoder node. So dense layer doesn't do much in terms of the computation, but a convolution has to do the convolution. So what you gain in saving from the number of nodes, you lose some of that in the extra computation that you're doing. But it's still one of the best things to use for images. So let's build our model, compile it. We can use a different optimizer just to show you what it looks like, and a loss of mean average error. And let's train it. You can train for 10 epochs and have some steps for train the data set. This should take some time. So now we have a lot of images. We made some patches, so it takes about like a few seconds per epoch. So let that run. And while that is running, let me show you like what we will do with the results. So once we get the training complete, and in real life, you would monitor the training and you would see if it is progressing properly or not, and we get some loss number here. And if it's not working, you would tweak things and rerun it. So we are going to go with whatever this thing outputs. Once you're done, you are going to, from the test data sets, you're going to take 3 items, which is take, and then you're going to predict, basically. So, and then I wrote this small little function to plot things. So we're going to plot the noisy image that is given in as for testing. We're going to plot the denoised version of it. We can also plot the ground truth of it. And then maybe just to see where the actual differences are, like what parts were able to recreate, what parts we did not. We plot the difference as well. So, so this will take some time. We just passed 3. And then this is our last function where we predict the image in the batch for prediction. And as I said, like we do this expansion to add the batch, because TensorFlow needs like batches to work on. Once you are going to data set handling, then you need to supply things in batches. So the expand dims basically add the batch dimension. Even if it is 1, you have to specify that. And squeeze is the opposite operation of the expand dims, where squeeze will remove the batch dimension. And so again, these are just quirks of the API for TensorFlow, so nothing basic, complicated. And you learn to live with it, and then you learn to use it. So there is another metric that TensorFlow provides called SSIM. So it is a little bit better than just doing the mean average error or mean square error. And I'm just printing it here just to show you what it might look like. So let's see. So a little bit more to go. Again, if you don't understand any of this, let me know in the comments, and then I'll try to answer those. So we have a question about the projector visualization. Yeah, so the ones that I was showing, that is visualizing the latent spaces in the MNIST data set. And there are ways to do that more efficiently, and I'll show you the link to go to a website that will let you do that. The idea is to actually look at the distributions in the latent space and see what is happening to your data. And oftentimes it's not easy to project things in 3 dimensions like that. They're good visualization tools, but it's a little bit hard to learn like what things are doing. So in any case, what you're trying to do is when you do classification, for example, you're trying to get all the ones together. You're trying to get all the twos together, so they form their own little distribution. And when you are looking for data, you're trying to recreate some data, it is going to approximate that distribution. So that's the whole machine learning is about, approximating distributions or sampling from a distribution that is close enough to the original distribution. So all the data that you had in the MNIST database, that belongs to some distribution. And even each individual numbers, they come from some distribution. Somebody's handwriting it is, and we don't know who it is. And it's a mixture of different people's handwritings, and they each might have its own distribution. The numbers themselves form a distribution, and then together it's a distribution. So if you get used to thinking in terms of distribution, then all of machine learning is about trying to find the closest distribution that you can find to the data, and then from that you're trying to find a single sample or sometimes multiple samples. And then we'll look at it in more detail, like how things happen in that way. And let's move. So looks like the training is done, and we are ready to do some prediction. And I'm going to execute this function. This is just a definition, so nothing happens. And this is where we are predicting, and it's just printing the SSIM, which is a measure of how close 2 images are. And now we're going to take those 3 images and plot variations of that, what we input as the noisy patch and what came out of it after the denoising, and what the ground truth is. So you can see it is getting closer. And it's not there yet, but eventually, if you train it for longer, if you adjust your hyperparameters and make the CNN a little bit more dense or with more layers, so you have to keep playing with the hyperparameters like that to kind of come to where the changes are, where you want to fix things. So the last row is the difference between the ground truth and the and the denoised image. So at first glance, it looks like it's doing amazing job. So there are differences here which you can't see. Okay, what I should do is maybe take this and there's no image invert. So what I wanted to do was actually try to invert it. Okay, so somebody find a good inversion thing, so it's not white on black, but black on white instead. So then you would be able to see the differences more clearly. So that's a denoiser. So as homework, what I would like you to try is more variations of this. So to do any of these, it's pretty straightforward. All you have to do is provide, like similar to add noise function that I had provided for adding noise to patches, you can use these functions I'm giving as example. So adjust saturation will adjust the saturation, and you can figure out how much you want to adjust, and then you have to clip it so that it remains within 0 to 1 range. Look up these functions, look up the documentation for these functions, and you should be able to train for any of these. And let's see, whoever does the best job, maybe what I'll do is I'll send you a book. So this is one of my favorite books in deep learning, and I'll send you a copy of this book if you the first person to send me all of these 4 things. So that's some incentive. So the in-painting part is a little bit complicated, but it's not. If you look at it step by step, all we're doing is we're taking creating a mask basically, and just adding a color to it, and then you multiply the mask with the image, and that will give you basically a hole in the image, and that's all. So that then where you have like small patches in the image, and that you can train to remove, and you can make like multiple patches in multiple holes in the image, and then try to recreate it. So that's that, and let's do something else. So all this time we have been training and trying to learn. So as you can see that as an individual sitting at home, you can either get a powerful computer or the graphics card that are so hard to get by, use them, or you can use the cloud, which we are using right now. But then if you want to do a big scale training, you have to shell out money to kind of get the time for more GPUs and train. So that can get expensive. So one idea is we can use other people's network. You can use other people's pre-trained network to solve our own problems. And we'll look at how to do that with an example about doing some facial recognition. So there is a model called MTCNN, which stands for multitasking convolutional neural network. And what it does, it excels at extracting face out of an image. And it can extract multiple different faces from an image. The way it works is it runs this cascaded HAR-like classifier onto the image, where it's taking basically the image and creating an image pyramid of different sizes from it, and then running essentially rectangular feature markers all around the image to figure out like if this is a face or not a face. All it does is it tells you where the face might be. It gives you the salient points on the face, which is coordinates for eyes and nose and corners of lips. So it's pretty good, and it has been trained for like on millions of images on public databases. So it knows about faces. It doesn't recognize them. All it does is says this is a face. And but it's pretty cool to be able to use that because you don't need to do any more training. It has already been trained on faces, and we can try to see how we can use it for doing actual facial recognition. So as a first step towards it, let's try to see how this might work. So we'll be running something called CV. It's a package for computer vision, which is really good, and it has Python binding, so we're going to import that. We are going to now download the MTCNN model along with weight. So this is a pre-made model that we are getting, and only bad thing is it only works with TensorFlow 1, so we changed the version to 1.x, but that's okay. So next is we are going to build a model. And now what I am going to do is download an image from the web and just show it. That's all I'm doing. So I'm now using CV to process images because we would need to draw on top of images, and Matplotlib is not the best to draw text on images directly. So we'll use CV. So we've downloaded this image from the web. Again, curl is a program that you can use to download any publicly accessible content. It just downloads it onto your computer. So in this case, the computer is the cloud, so it's probably somewhere on my cloud machine. So you can look at it. It's probably somewhere here. So this is actually a full-fledged Linux machine running here, and it downloaded this file. And we show the file, and it's basically a big montage of many of the Disney characters. And we are now going to run MTCNN on this image. So again, it's not going to tell you who it is. It's just going to figure out the faces. So the way it works is you just give it the image and call this method detect faces, and it will find all the faces in that image. Remember, this is just one image. It's not multiple images. So within one image, it is then going to, for each face it has found, it is going to give you a box, which is the XY corners of the left corner, and then the width and the height. And then what we are going to do is just going to draw a rectangle to tell you that where it thinks the images are. So that's all this does. So let's do that. So for some odd reason, CV operates in BGR, so we have to convert that to RGB. And let's see if it recognized any faces. So it looks like it did a pretty good job. It recognized most of the faces. I can imagine like this is trained on human faces and not on cartoon faces, but it is still pretty good at finding out faces, and not just like finding out, but like it's giving you the rectangles that very closely match the face. So it's done a great job. So some of the places where it failed to find a face is this character on the right. Obviously it would fail on that. That doesn't even look anything close to a face. I'm not sure why it failed on this character from Up. And this one, I think it's from Tangled. So it works well, and that's what we'll use in part 2 of our facial recognition system. So now we have to figure out like how to match this to a known face. So what I'll do next time is we will do the full facial recognition. We'll use MTCNN as part 1. So now we'll use another trained neural network to do part 2, which is actually recognize the faces. So what maybe what I can ask you to do, if you can, send me 2 images of yourself in like different times, different poses, and we'll try to use one for as ground truth, another to find out if we can recognize a different pose of you. So just face images just like this, portrait size. Small images are all we need, like even this big is enough. So if you can, either LinkedIn or Twitter, just send me 2 images. And if I get enough images, we can do the training and the recognition live. Otherwise, I'll use some canned images that I have already. So that's how you use other people's network and save time on training. So the main thing is they have to be general enough. So like this one just recognizes facial regions, and they have to work on your new training data. So you can't just use it on animals, for example. It will not work probably, or it will not work as well. So without training, you can still use other people's network for good use. And we're going to use 2 of these to solve an actual problem, which is of facial recognition. So going back to our slides. So I talked a little bit about distributions, and I think what I want to do in the next 9 minutes, so I'll cover the variational autoencoders maybe next time, but let me cover GANs because we talked about it, and Ming-Yu talked about it as well. So what are GANs? So GANs are similar to variational autoencoder, which we'll cover next time. Autoencoders, variational autoencoders, they kind of estimate the variance and the mean of a distribution, but GANs directly sample from the target distribution. So that's like more of a mathy difference, but they are also put together very differently. The GANs came about from a presentation a few years ago, which Ming-Yu based his GauGAN on, and then a lot of other research papers came along. But the idea is so straightforward now, if you look back in retrospect, that you take a random image, by random meaning it's just noise, and you try to train it to basically become an image that is similar to one from the sample. So you have a training set, which is the set of sample images, say all cats or all dogs, and then you start from a random noise, and then you progress it over time by training it in a way where it starts to kind of generate an image of a cat or a dog or a butterfly. Essentially, when you have equilibrium, you will start getting images from that distribution that are indistinguishable from the original distribution. So that's the idea. So how do we do that in practice is there are 2 networks, essentially. They're connected back to back, or in a way which achieves this. So the 2 networks are called the discriminator and the generator. So this is your training set of real images that you're going to feed to the discriminator. And all the discriminator does, it's a simple classifier. All it does, it tells you if the image is real or not real. It's real or fake. And from the other side, what you're going to do is take random noise and feed it into the generator. And whatever the output comes out of the generator, you are going to try to run it through the discriminator. So when your discriminator is trained on, say, images of cats, if you feed it noise, it is going to reject it, right? So because it's not real cat, so it's just random noise. But the way these losses are connected to each other over time, the generator is going to start generating images of cats, and discriminator is going to have a harder and harder time to discriminate between real images and fake images. And at some point, they will reach an equilibrium where discriminator basically cannot distinguish anymore whether the image is coming out of the generator or it's a real image. So that's when you stop it, basically say, okay, I'm done training this now. And then you can put random noise in as many times as you want, and out of the network generator, you get images that are indistinguishable from real images. So the two main things are that they are connected together. So it's not the training is not happening in isolation. And secondly, you can't just train one at a time, because the discriminator will get very good if you just keep training it. So you train for a few epochs the discriminator, and then you train the generator. So you keep switching between the two, so that you are getting the losses from one, and the resulting mixture is being fed into the other one. And as you keep doing that, at some point you'll reach equilibrium. So that's the general idea. Any questions about GANs? So just to reiterate, I'll just go over this in a more of the, you'll have the slides so that you can read as well. So again, the goal is to generate random unseen cat images. You need a classifier, and that's your discriminator. You need a generator that generates random images. Then starting input is always noise, and you hook them up together. And let's see how it works in practice. So again, import TensorFlow. We're going to use an image IO to process image. And this example, by the way, comes straight from Google. So we'll use this because it's faster to train, because it's using the MNIST database, but now as a data set. So okay, so the generator that we said is going to be a simple thing that takes in noise and essentially just adds in a bunch of nodes till you get the output shape that you need. So it's not doing anything complicated. All it's doing is taking some random numbers, and it's kind of expanding them into a shape of the final image, which is what we want, is 28 by 28. That's the target size of the MNIST data set. And you can have a big complicated network, so you distribute your weights accordingly. And essentially this is what it does. So it starts with a dense layer, and I'll talk more about these batch normalization and leaky rectified linear unit. These are just optimizations, and then there are features of GAN which kind of make it prone to mode collapse, and even sometimes you get this exploding gradients or vanishing gradients. So all those issues happen with GANs, that this batch normalization essentially normalizes the weights around each of those layers. And the leaky rectified linear unit, what it does is sometimes when the left part of the rectified linear unit, imagine that was the straight line through zero, and the second part is the angled line. The left part, when it is zero, its derivative is zero, so that vanishes away. So leaky rectified linear unit essentially just adds a little bit of weight in that particular case. So again, don't have to worry about this. Just imagine it's just a rectified linear unit. So here, and so don't confuse the con-TD transpose with the convolution. So this is, you can think of this as a reverse of a transpose, a reverse of a convolution. So all it is doing is, instead of collapsing data, which convolution 2D does, it is expanding the input data. So we keep expanding it until we get to the shape that we want. And you can also achieve the same thing with an upsampling layer. An upsampling layer simply duplicates pixels as they get bigger. And Con2D transpose does the same thing, but does a convolution in between. So this kind of averages out. So all we're doing is taking random numbers, and then what we want is just a dense network of weights so that things can be learned. We're not doing anything complicated here. It's just trying to create as many nodes as possible from the original noise that comes in. And we'll build a generator. Didn't get executed. And we'll build a generator and then try to see what happens to it. We are feeding it basically 100 random numbers, and then running it through these essentially 3 Con2D transpose node. So this can be slow, but we can keep looking at it. And we make the discriminator. So discriminator is essentially just a qualifier. So output is just a dense, whether the image is real or fake. And otherwise, it's just a convolution network. And these dropouts are ways to kind of avoid overtraining. So you basically set the weights of random 30% to be 0 so that you don't overtrain. So again, these are just techniques for optimization and to train your network better. And we build the discriminator, and all it gives you is a number, either negative or positive, based on how close to the input the image is. So if it's random, it will be 0. If it's from the distribution, it will be 1. If it is not, it will be 0, -1. So next part is the losses. And because we're running out of time, I'll cover the losses next time, but you can run this and try to understand what it is doing. So it's essentially doing what I described earlier, is setting it up for so that we want the discriminator to kind of, when it is trained, start failing, that it won't be able to distinguish whatever is being generated from the real images. So that's the loss you would set up there. And in the generator, the loss would be the reverse of it. You want it to succeed when it is as close to the real images. So that's, I think what I want to do is probably stop here so that, so play with the GAN. And here are some examples of advanced implementation of GANs. This is the work of Ming-Yu and his team. And actually, I can bring this up quickly. So this is an example playground of what his research did. So you have these 2 areas where all you have to do is paint, and it will try to generate from that. And it did. So you paint different areas, basically providing this guided input to the network instead of random numbers. And you can make a so we can convert this to a beach here by simply drawing for sand. So let's make a nice beach here. As you can tell, I'm not an artist. I work with artists every day, but I did not learn any art. So let's make this patch of sand, and there you go. So we have a beach now. So play with this. It's pretty fun. The interface could use some work, but it's awesome work. So try it out. And let's wrap it up for today. We're gone 4 minutes overboard, but hope that's okay. So next class, we will finish our facial recognition. If you send me 2 pictures of yourself in different poses, and also try to make it hard, like do one from like top or side or something harder for it to succeed. And then we'll explore the latent spaces. If somebody had asked the question, like, can we see those networks or the distributions in a 3D space, and I'll show you how to do that. And we'll cover RNNs and transformers. So transformers are all the rage now, so we'll learn more about it from the creators of the transformer next time. And you can also try to use the GAN example and generate satellite images instead of handwritten letters. Because all classes that I've taken on machine learning, they usually train on MNIST, so you want something different. You try the ones on satellite images, so you already have pre-classified satellite images. Let's see if you can generate new satellite images that the network doesn't have at all. All right, so let's stop here. Any last questions? Otherwise, I will see you next week. Okay, so this question about in-betweening with CNN. So yeah, so the pixel, everything is image-based because all data needs to be numeric. So if you can specify the stroke numerically somehow, we can still train for it, but otherwise you would have trouble because if the stroke is a continuous thing, it's hard to break it down into discrete data. But there are ways to represent your images as strokes and then convert it to numerical input. Then we can train on it. But usually, yeah, everything is CNN. With CNN is always pixel-based. So is it for the GAN you're asking that the noise taken is normal? Probably. So in reference to the GANs, yes, it is important that we take from a known normal distribution because we want all these things. The differentiation needs to be continuous. And what we're trying to do is kind of shape one distribution into the other one. So it does start from that assumption. It is possible, but it gets really hard. So I think all the programs and the APIs, they are designed to operate with the same size images as batches because you're training in batches. Imagine you're training like billions of images in batches. So you don't want to have any hiccups or any issues. So what most people do is they will either crop or readjust or pad images. Also, many of these algorithms should be invariant, especially CNN based to transforms. So you can transform your images and it should still be okay. And I think that's a great point about like learning from images, that you can do a lot of data augmentation prior to create even more data for yourself. Yeah, usually you want it to be as efficient as possible, make your images all the same sizes. Right, I thought that's what he meant by resolution. So the images have to be the same size. It all depends. I think the one we are doing with the MNIST has 60,000 images. There are other issues with GAN. Sometimes it doesn't work and you tweak something and it starts working. So in general, it does take a lot of images to train with GAN. Because imagine you're creating from random image something to the distribution. So to train that and to get to that, it does take a while. All right, let's stop here. And sorry for going a little bit over time, but I think we covered a lot of stuff today. So send me the pictures and we will learn to do facial recognition next time. Bye.
At SIGGRAPH 2020, more than 10,000 individuals from 95 countries gathered virtually to experience over 350 hours of content presented by more than 1,600 contributors. What resulted was pure SIGGRAPH. Robotic advances use subtractive fabrication techniques to carve foam and similar materials like an artist. Modeling and predictive computation creates a more robust and accurate time-stepping of nonlinear elastodynamics. New investigation into damage simulation could change the landscape of video and game effects, as well as surgical training. Novel healthcare technologies point toward new ways to transform and enhance lives. Research will help users to create reprogrammable multicolor textures made from a single material. AI-driven technology pushes the capabilities of crowd simulation. Award-winning animation showcases the latest in computer graphics. Real-time and gaming technology advancements transform interactive storytelling techniques and explore new applications of the technology. Evocative digital artwork uses machine learning to create visceral experiences. Now is the time to share your research, your innovations, and your creative inspiration. SIGGRAPH is your community, and we hope you'll share your work with SIGGRAPH 2021.